Welcome to the presentation for the paper titled Grounding Aware RRT Star for Path Planning and Safe Navigation of Marine Crafts in Confined Waters. My name is Thomas Enevoldsen. I'm a PhD student funded by the Shipping Lab project at the Automation and Control Group at the Technical University of Denmark. My co-author is Associate Professor Roberto Galeazzi, who is also from the Automation and Control Group at the Technical University of Denmark. An annual report by the European Maritime Safety Agency shows that human error accounts for 44% of all accidents which relate to contact, collision, and grounding. Furthermore, another study showed that grounding incidents often occur due to poor situational awareness or assessment, which also relates to the suboptimal usage of available equipment on the bridge. A prime candidate for reducing or completely diminishing incidents due to human error is through highly automated systems or advanced decision support to aid against collision and grounding. There are two main categories within collision avoidance: open water and confined water collision avoidance. During open waters, the vessels have to some extent unconstrained possibilities for avoiding a potential collision situation due to the open playing field. At open waters, collisions are avoided at all costs while adhering to the call regs. However, doing collision avoidance in confined waters, there is a trade-off between both avoiding collisions while adhering to the call regs and also while trying to avoid grounding. This paper has an emphasis on collision avoidance in confined waters. The paper presents two central contributions. Firstly, the paper presents a marine-oriented sampling-based motion planning framework for operating in confined waters. A sampling strategy for directly sampling the depth contours is presented in order to increase its efficiency. Furthermore, the framework leverages a specialized grounding-aware cost function. The cost is the second contribution, where based on historical data, the prior best practices of navigators has been quantified. This results in a learning-based cost function which directly encodes navigator-like behavior for traversing confined waters. The proposed framework is then successfully demonstrated on two confined water scenarios. It is assumed that owned ship is a larger vessel, which is restricted primarily by its draft. It's also assumed that the vessel has an underlying track control scheme which utilizes waypoints. The target vessels are assumed to maintain constant course and speed whenever they're in a stand-on scenario. Furthermore, an elliptical comfort zone is placed around a given target vessel to describe a no-go zone. The coming slides will revolve around presenting the four building blocks of the before-mentioned marine-oriented sampling-based motion planning scheme. First, the proposed sampling scheme will be presented in detail, then the constraints which lead into the grounding-aware cost function, and finally some high-level information regarding the optimizer. It's important to note that the proposed framework isn't exclusively meant for RRT star, but will work for any optimal sampling-based algorithm such as batch-informed trees or fast-marching trees. Firstly, the proposed sampling scheme. This slide shows the extraction of real ENC contours. The leftmost figure is the extracted contours once a geofilter has been applied, where the right figure shows the cropped contours. The yellow region indicates land, and white indicates shallow waters for drafts of 6 meters or less. Therefore, for a vessel comfortable with sailing at a depth of 6 meters, all the blue contours are valid. As you can tell, this region is highly non-convex with several holes. The state-of-the-art in sampling-based planning for marine systems is to simply sample the rectangular approximation of the area. This, however, is highly inefficient, primarily due to the rejection rates as the ratio of shallow waters to feasible waters change. We instead propose directly sampling the depth contours. Since the polygon data is directly available from the charts, one can apply techniques from computational geometry. The feasible depth contours are joined into a single non-convex region with holes, which is then triangulated. Each of the resulting triangles are then uniformly sampled by area and each selected triangle is then uniformly sampled. This requires 3 calls to a uniform distribution compared to the usual 2. However, despite an additional amount of computation time for both generating and sampling the triangles, once the triangulation has occurred, the efficiency of the triangulated scheme significantly outperforms the regular uniform sampling scheme. The table below compares the setup time for the 2 sampling schemes within 2 separate regions. The blue curves compare the performance of the triangulated scheme to the rectangular uniform scheme on the environment shown on the right-hand side. Here the ratio between the rectangular approximation and the feasible depth contours is 2/5. The triangulated scheme is close to constant since all samples which are generated are guaranteed to fall within the region, whereas the rectangular scheme must reject a majority of the samples. Now that the sampling scheme has been selected, the next part of the framework is to consider the system constraints. The collision avoidance problem has 3 major constraints: environmental restrictions, maneuverability restrictions, and call-reg compliance. The first of which is dealt with by performing point-in-triangle tests along the computed path. This ensures that all paths are feasible with respect to the depth contours. The second is achieved by constraining the distance between 2 subsequent waypoints, as well as maintaining a minimum angle between the 2 legs. And finally, call-regs compliance is achieved by rejecting samples that create a rule violation. This is primarily achieved using relative bearing and CPA and TCPA. Please see the listed reference for further details regarding the maneuverability constraints and the call-reg compliance. Exploiting AIS data for encoding behavior has been explored to great extent. It's a very hot topic at the moment within both trajectory and behavior prediction. We instead propose utilizing the AIS data to encode a region of safe passage and thereby encoding the best practices of previous navigators into our cost functions. In order to do so, we require a set of AES messages as given on the slide. Each message consists of the listed entries, with the most essential for our purpose being the coordinates and draft. We limit the set of AES messages based on speed to exclude stationary vessels as well as rescue helicopters, and by geographical region. The reduced dataset is then used to compute a multivariate kernel density estimate, which is in this case a 2-dimensional KDE. The KDE is a non-parametric estimation scheme which estimates a distribution f, which the provided data is sampled from. This distribution is of course unknown. For such a KDE, the choice of kernel function k and bandwidth matrix h act as tuning parameters. We chose the commonly utilized Gaussian kernel and then hand-picked the bandwidth based on the chosen geographical region. The resulting estimate of the underlying distribution f hat is then given as in the marked box below. This slide shows how the kernel density estimation has been applied to the selected AES data. This example is from the Little Belt area in Denmark, and also in the paper a case study from the Great Belt area is included. The left figure shows the raw AIS data, which is captured over a 1-year period within this area. The rightmost figure shows the computed KDE, which uses all the data points from within this region, where the draft is greater than 3 meters. The blue contours show the corresponding feasible water regions, whereas previously the white regions are shallow waters and the yellow regions are land masses. As we further constrain the draft, it is clear to see that a navigational and behavioral pattern is emerging. As the draft size increases, the vessels maintain a greater and greater safety margin from the shallow water contours. It is also clear to see that most vessels follow the same path on the west side of the shallower water region in the center. The proposed sampling scheme and KDE-based cost function can then be combined with an existing sampling-based motion planner such as RRT star in order to create what we call the grounding-aware RRT star algorithm. As previously mentioned, RRT star is just one of many possible algorithms for solving the generalized optimal sampling-based motion planning problem. The overall inner workings of RRT star is then presented in algorithm 1, where our proposed sampling scheme, constraints, and cost function modifies the relevant parts. The cost function consists of two parts, namely the minimization of the path length, which is shown in the blue box. This is given by the current path sigma evaluated with an L, which is the Euclidean distance, and the grounding awareness, which is given by the red box. This is then the current path evaluated in the computed KDE. Each term is then scaled by omega 2 and omega 1 respectively, which represent scalar weights. We then evaluate two scenarios where this grounding-aware RT star is used for collision avoidance. The left figure shows the case study from the Great Belt area, where the own ship is southbound and a target vessel is northbound. The yellow trajectory is the optimal trajectory if only path length is considered as an optimization criteria, where the green trajectory combines both path length and KDE. The yellow trajectory, as expected, completely disregards the potential navigational safety hazards of navigating too close to the contours, whereas the green remains within the center of the feasible area throughout most of its journey. Both trajectories obey the call regs in the head-on scenario and adequately performs a collision avoidance maneuver. A more interesting case is the one from the Little Belt area. Here the yellow trajectory computes an obviously shorter path, but this shorter path is clearly unsafe and poses a huge risk of grounding. Using the information within the KDE, the proposed method is able to remain safe whilst also performing this call reg compliant overtaking. And it also remains within the region deemed safe by past navigators. For this final scenario, it's very obvious that the information encoded within the KDE is an overall behavioral trend, since the KDE contains no information about going on the east side of the small island at the center. It instead moves all the traffic west around. And finally, to conclude, the paper proposes a optimal marine-oriented sampling-based algorithm, namely grounding-aware RT star, which successfully demonstrates the ability to perform both grounding and collision avoidance. The proposed sampling scheme for confined waters shows a significant performance increase over the traditional rectangular sampling scheme. We are convinced that for even more complicated confined water scenarios, that triangulating the depth contours will provide a significant performance boost. Furthermore, it is shown that multivariate kernel density estimation is a valuable tool for both quantifying and encoding the past experiences of navigators. This use case scratches the surface of potential ways of exploiting past experiences for grounding awareness. Thank you very much for listening. This research was done as part of the Autonomy Work Package of Shipping Lab. I would like to thank the Danish Innovation Fund, the Danish Maritime Fund, and also the Lauritsen Foundation. And finally, I would like to thank the Danish Geodata Agency for providing the sea charts.